Thank you. I'm, I'm not, I'm not so much going to be talking about the past, but what's needed for the future. Obviously, I can't talk about what's going to happen in the future exactly. But I'll give an example. I gave this example earlier, so that's why I'm calling it a recap, but this is a very quick recap. If neural networks are better than humans in a great number of tasks. They're very good at recognizing images, but not all the time. In particular, the most extreme example is when there's what's called an adversarial attack. Under an adversarial attack, you can cause a neural network that's imitating a cat to see a wolf and make it think it's a mouse. For people that aren't directly in the field, that's really shocking. How could that possibly be possible? Well, and also, why does it matter? Why is it important? Well, as I said, this particular example is due to adversarial attacks. But the point is that this is a symptom of the fact that even the largest neural networks lack the common sense. My other example was a mouse misrecognizing a cat as cheese. So even biological nervous systems are doing something that our artificial neural networks are not doing. And I'm not sure if I want to call it common sense when it's a mouse, but anyway, more limited goals, and in particular for what we can achieve in the near future, is a step in the direction of common sense. It's something I'm calling sensibility. And I'll talk about that some. But the reason that the adversarial attacks can succeed, or in some instances, just random changes could succeed, is because it's not even limited to deep neural networks. Any AI system, or any classifier system, if the output of the classifier system is a differentiable function of the input, and say it's an image, 1,000 by 1,000 image has 1,000,000 pixels in it, you change each of those 1,000,000 pixels by a very small amount, call it epsilon, but if you pick exactly the right direction for each of those, which sign, whether it's a positive sign or a negative sign, the total change in the output can be 1,000,000 times epsilon. Well, that's pretty catastrophic to a recognizer. And furthermore, there are defenses. For the adversarial attacks, there are defenses, but they aren't perfect. And furthermore, every time there's a good defense, somebody comes and says, better attack, because they now know that defense and they can specifically attack that defense. So it is something that's important, but it's actually a symptom of something much larger. This is just saying the thing I said already about how it's possible. And this is actually just writing out the equation. So I'll save time by skipping that, but it's in the record, so you can look it up if you're interested in that particular part. Why is it urgent? Well, because part of why it's urgent is not only because AI systems are so good, but because they're improving so rapidly. That means they're going to start taking over more and more tasks in the world. And one of the tasks they'll take over is designing the next generation of AI systems. That's already starting. But if the system making the design, it doesn't have common sense, how can we get common sense into the system being designed? Well, one thing is something that Tom Mitchell mentioned in a lecture, at least something like 10 years ago. Let's have teams, cooperative teams of humans and AI systems. Then the total team has at least some common sense. I mean, not all humans have common sense all the time, but we're moving in the right direction. So this is just a thing I already said. I'll just get the next generation of AIs. If they're not sensible, how can, it just goes downhill from there. So I'm proposing a grand challenge. I won't read all of these because they all will appear later. I have five slides that are talking about things where we can already get started. And the ones that's what the numbers are in this slide. And the things that have a particular number will come up in the top of that slide, and so I won't read them here. But I wanted you to see the overall picture. So first, ethical AI. Now, I won't really talk in detail about ethical AI, but being sensible, being able to interpret what's going on, what I call holistic interpretability. Being able to interpret an inner node of a large deep neural network and understand it in the context of all the other nodes and of the total system. Those and the other things I'll talk about will contribute to ethical AI. I won't talk about specific techniques specific to ethical AI. So sensibility is the one I've already mentioned. That's the most important one. But the thing that I mentioned about the adversarial attacks means that you're vulnerable to having a non-sensible answer, that the network has no realization that it's not sensible, is due to the fact that the derivative of the output can be computed all the way back to the input. Well, that happens to be the way that neural networks are trained. It's called gradient descent, because you're computing all these derivatives simultaneously. When you have multiple derivatives, it's called a gradient. Don't even need to know calculus, but that's what it is. It's the simplest rule of calculus, how to compute these derivatives. But now I've lost no controls from this source. So I'm reading my slide from here. How many have we missed? I don't know. You saw the grand challenge slide. Okay, so you only missed one. I don't know what's happening here. Can you see the slide on the screen? Oh, okay. So I'll just, my slide and the screen are in agreement. So so I'll proceed, even though it's not up on the prompt here. But it's not obvious, and I didn't even think of it I've been thinking about this for some amount of time before I realized it's not that we can't use gradient descent. Getting rid of gradient descent is neither necessary nor sufficient. The problem is if we depend only on gradient descent, then you have this vulnerability. We need to introduce some techniques that don't depend on the output being differentiable. Now, one of those, or if it's differentiable and the derivative is 0, that will also be okay. I may have time to talk more about that at the end, but I put that at the end because it's a technical thing, and if I run out of time, I'll leave it out. So the first idea, getting started, well, first, ethical AI has already started at a number of institutions, so I just filled that in. But the idea is to incorporate what I just mentioned. If we have within the network things where the derivative is 0, the adversarial attack stops because the derivative is 0 can't figure out can't get back to the input. But also gradient descent can't get there either, so we need to work around for that. But but we've started on that. We're already starting to brainstorm ideas for doing that. Another idea, I don't know why this one doesn't say number 2, but this is, I guess maybe this is second part of number 1 or something. Semi-automated knowledge engineering. That ties in with what I borrowed from Tom Mitchell, but it's more specific. Knowledge engineering is humans participate in putting human knowledge into the system. And human knowledge is not so easily differentiable. It is if you represent it as a differentiable function, but if you can figure out some other way to get it in, we can make some improvement on sensibility. Number 2, similar is what I call human-guided training. At least from my time starting in AI, that's more controversial than the knowledge engineering. Knowledge engineering was used back then. Recently, it's been eliminated in some deep neural networks, in particular in speech. You can do an end-to-end complete neural network with no human knowledge engineering. But that's, relative to the sensibility issue, that's actually a bad thing. But human-guided training was always not allowed in AI because if the humans actually are guiding the training, the human intelligence may get, in particular, when people were writing the actual code that makes the decisions, they could sneak in human knowledge in the code. So, and people would try to avoid that, but critics would say, how could we be sure of that? You wrote this very complicated code we can't understand. We're not even programmers. But so there was a tradition not to do human guidance during the training. We don't need that anymore. We don't need to prove that deep neural networks are very smart. They're not always sensible, but they're very smart. So human-guided training is another thing that we can get started. Another thing I mentioned, colleagues here at Carnegie Mellon, Bikshit Raj and Rita Singh are already helping me with brainstorming, and we've thought of a particular example. This is a speech symposium. The example is, but it's mostly speech recognition. But we wanted to have examples so that we could write lesson plans for student projects. So we wanted something easier than speech recognition. Also, it's easy but it's actually a computer vision problem. Namely, take a picture of speech, which is called a speech spectrogram. The speech people here all know what that is. Everybody else, it's a picture of what speech looks like. It's what it looks like to the computer. But now the task is, with human guidance, teach a computer to do better visual recognition of this spectrogram. Now we know that's a hard problem because actually people at Carnegie Mellon and elsewhere worked on that, trying to do that in the speech recognition, within the speech recognition systems. And we have some of those experts here today. But now, with the deep neural networks, if we can learn to put human guidance into the training of the deep neural networks, we hope we can move forward on this goal. Whoops, well, I just pointing out, it's a computer. Don't think of it as a speech recognition task. We're deliberately leaving out the language model because that's just too big for a student project, in our opinion. So just recognize the sounds and the syllables and maybe the words, but don't try to get the whole sentence. Now, as mentioned in an earlier lecture, humans can read spectrograms, some humans. Victor Zuk can do it very well. But furthermore, human guidance in the training of a neural network that has 1 billion parameters, that's beyond human labor. But it's semi-automated. Use the AIs to help automate the process of human control of the training, or human partial control of training. It's a cooperative effort controlled by the AI and the human. And then that's the way we're already starting in the sense we're starting to get up lesson plans for things that could be student projects for this example. But another thing is, AI systems, when they're wrong, they don't know that they're wrong. Now, there are exceptions to that, but by and large, they're not concerned with introspection. Well, that's actually a problem that I thought about a couple of years ago, so that's not something I'd worked on even before I was thinking about this current grand challenge. And what I figured out was that if I put in a node that's doing introspection on another node, what happens in the neural network when you do this back propagation of the derivatives, both of these nodes start trying to, depending on how you have the plus and minus signs in the weights, they're either trying to predict what the other one is doing or trying to predict the opposite of what the other one is doing. But that means the node that you're trying to do introspection on is constantly changing because you're watching it. Doesn't work. The trick was, and this also is relevant to what I was saying about doing something other than just using backpropagation. You have a forward connection from both of these nodes. You have to do that because you're comparing them. But you don't backpropagate back to the subject node. You just go in, and that's why I say I don't want to use autograb, because autograb, if you do a forward computation, it always computes a backwards computation. Here we intervene in the backpropagation and cut off this connection. And now you can actually have this introspective node. That's oversimplified, and obviously for the longer goals, it's still a long way away, but it's a start. That's all I'm saying. Another thing that I've been working on that's not common, because Microsoft, for example, has enough computers so that if they want to build a 1,000-layer neural network, they just build a 1,000-layer neural network. Well, I was working at home on my home computer. I mean, I had multiple GPU cards. I could do a significant amount of computing. But I was working with smaller networks, and so I worked on being able to grow the network gradually. Well, again, if the network isn't finished, then and you have introspection, among the things that you can fix is the things that would cause nonsensible errors. Maybe. I am not there yet, but we have tools for which that might be possible. And then this is another one this is a invention I did a couple of years ago for a different purpose. But it has it's what I call knowledge sharing between nodes. And the knowledge sharing is very flexible, and it has hyperparameters. So this is one of the reasons we need this cooperative human-machine control, because the number of these links, and these links are not connections. They're not connections in the network. But they are links, and relative to the network, even if it's a non-recursive network, you can have the links either going upwards or downwards. They're not connections, so you don't get the circular computation that you would get with connections. But they superimpose a regularization that's different from the backpropagation. So that's a side effect, but it also fits with one of Jaime Carbonell's manifesto for continual learning. One of the things he said was, at least that point in time, I'm actually stayed up to date on it, but at that point in time he said that the systems that tried to learn new things, continually, lifelong, continual learning, one problem is that they may tend to forget things that they already knew. And in fact, it might be a catastrophic thing that something really important they might forget. And people didn't really have a good enough solution for that. Well, this knowledge sharing, it goes not only between nodes within a network, but it can be between nodes within two separate networks, or a previous network and a new network that doesn't even have to be the same architecture, but for which you have some mapping between nodes for which it's reasonable to make a link. Now, how much time do I have left? A little bit? Okay. This is, I mentioned if you have, if the derivative is 0, then you can't backpropagate any change in the output. You also can't backpropagate the objective function of the classifier. But the original, I actually started in neural networks before I started in speech recognition. But I failed. But what I was working on was something called a perceptron. And a perceptron is just one of what's called the activation function. The function in a single node is 0, then a step, and then it's 1. Well, the derivative of 0 ever exists. At the discontinuity, there's no derivative. But what I wanted to bring up is the fact that perceptrons in recent years, for most of the past 20 years, perceptrons have been, and even though deep neural networks are sometimes called multi-layer perceptrons in honor of Frank Rosenblatt. But he's misquoted. He's misunderstood. The following passage from Wikipedia is wrong. Now, Minsky and Papert, I started with the Minsky Papert book, so I know that book. And this says they show that it was impossible for these classes of networks to learn the XOR function. Not true. Minsky and Papert did not say that. Minsky and Papert did not believe that. And it's also a false fact. It's because somebody taking the name multi-layer perceptrons thought that a single layer of a neural network would be a perceptron, and started calling it a single-layer perceptron. But if you go back to Frank Rosenblatt's definition, which Mitzi and Papert also used, a perceptron has as a minimum, in other words, Rosenblatt did some more complicated things, but the elementary perceptron had a set of sensory nodes, a set of associative nodes, and a set of response nodes. Well, response nodes are like the output, the sensory nodes are like the input, the associative nodes are the hidden layer. With a hidden layer, you can compute the XOR function. In fact, Rosenblatt proved a theorem that you can compute any Boolean function. Somebody said, well, Rosenblatt was just wrong. No, he wasn't wrong. The proof is simple and obvious, actually. I'll leave the proof to the audience, but I'll give you a hint. The number of associative nodes is not limited. Take 2 to the n associative nodes and figure out how you can compute any Boolean function. Some of you probably got it instantly. Some of you will have to go home and think about it. But it's a true fact, and it was not Frank Rosenblatt's fault that it got misrepresented. So perceptrons, if we can finish the problem that I didn't finish back in 1960, we can include them in our neural networks. And not only that, but other things. So that's it.